Hi, everyone. Thanks for joining the Protocol Labs Research Seminar Series. Today's speaker is Alfonso de la Rocha. Alfonso is a research engineer here with us in the Resilient Networks Lab at Protocol Labs. Before joining us, he worked as a blockchain expert at Telefonica R&D, where he was responsible for the design and development of core technology based on blockchains, distributed systems, and advanced cryptography. Alfonso's involvement in research and development began at, oh boy, Universidad Politécnica de Madrid, where he worked on topics related to energy efficiency in data centers. His broad research and development experience also includes research into the compression of video coding standards at Ericsson Research and projects related to securing inter-domain routing protocols at KTH Royal Institute of Technology in Stockholm. His talk to us is about protocol stack for the Federation of DLT Networks. Alfonso, I'll let you take it from here.
Thank you very much, Jonathan. Thank you for having me here. So today I want to share the last research I did in Telefonica before joining TL. And I'm going to talk about a corporate environment in which we are not maybe that used here in TL. So please stop me in any way if some of the assumptions don't make sense to you or whatever. So I'm going to talk about protocol stack for the Federation of DLT Networks. But first, I'm going to explain why we embarked on this research. So I don't know if you know how it is the deployment of DLT networks in right now in corporations, but what it ends up happening is that it could make sense to deploy in using blockchain or a DLT network. What they do is they deploy their own network in the platform of choice that suits their needs, and they deploy, for instance, their corporate bonds issuing use case. What happens is that they end up having a network just for that use case with a small number of nodes. Then we have another use case in which we are a set of telco operators and we are going to fix our roaming settlement, but we choose Hyperledger Fabric because of its additional features to Corda, and we end up having another network, deploying another network with a small number of nodes and just for this specific use case. In some cases, we can have sector consortiums that deploy their own networks, but they end up not having more than 20 nodes. And we have like big general purpose consortium networks that are permission networks. They try to be semi-public, but no one ends up deploying corporate use cases in them. And then we have public networks that corporations escape from them because they don't comply in several ways with regulation. They have scalability concerns, and in the end they just use it as a complementary infrastructure, but they don't end up deploying the use cases there. So in this context, what we realize is something that everyone knew, that there's a trade-off between scalability and security, and in corporations they end up going for the scalability instead of for the security. So for instance, the corporate bonds use case, they end up having a small number of nodes in order to comply with regulation, and also in order to be fast and be able to accommodate all the traffic of their use case. So what happened is that we ended up deploying networks just for a specific use case in order to fine tune for that use case. And we ended up having in our infrastructure several small networks with a small number of nodes, and then the security problem. Like it's really easy to collude in these networks with 3 nodes and impact the data integrity of the information that we store in this network. And this is why we started this line of research in which we were trying to ensure data integrity in networks with a small number of nodes, so that even if there was a collusion between the nodes of a network, between a majority of nodes in the network, we are still able, being a minority in the network, to be able to show that the information that we store is consistent with the history. And as we couldn't deploy a general purpose big network with a lot of nodes in order to give this security, we came up with the idea of, instead of building a general purpose network, let's try and federate all these small networks so that the small networks can leverage the number of nodes of other networks to ensure the data integrity of that they store in their own network. So this was the idea. And the requirements that we had for this is, first of all, we required this protocol stack or this federation to be agnostic of the platform, because we ended up deploying different DLT platform according to the use cases and according to our needs. So we wanted these protocols to be completely platform agnostic. Our main focus was to offer data integrity. So if we have a small network of 3 nodes, and this is a level of security, colluding in that network is easy, we needed a way in which we could leverage the nodes of other small networks to ensure the data integrity of our network. And we wanted to do this in a collaborative way, so that the more networks that joined our federation and the more nodes that joined our federation, the more security we could potentially give to our stored data. And then this is not in the scope of this talk, but we became ambitious and we said, okay, once we have a federation of corporate networks, DLT networks, we could even try and standardize these protocols so that we could have some kind of interoperability between these networks. But to the time that I left, we didn't make any big leap forward in this sense. I will mention it briefly in a moment. So what were we doing and others doing in order to have this enhanced level of security or data integrity in these small networks? Some people, what they were doing was to use sidechains. So in order to comply with regulation, in our small network, we do some of the processes that need to be private and the logic that needs to have scalability in our network, and then dump certain parts of the logic into a public network or one of these general purpose consortia networks. This was a one-to-one relationship, and it wasn't that secure in the sense that it had to go out off-chain and then make the communication to the other network on-chain. Others what they were doing was to do public snapshots in different networks, so that you have your storage in your network, and what you do is make photographs of the state of your storage at different points in time, make a summary of it, and dump it into Ethereum or any other public network, so that you had there like a backup of how was your ledger in that specific moment. The problem of this is that you needed to do some kind of summary or cryptographic summary in order not to leak private information. And you couldn't, one of the reasons we didn't go with this for a long time is that you couldn't predict, once you play with public networks, you can't make a certain cost model of your system because of the volatility of the price. So when you go to your finance department and ask them for money for cryptocurrency, they end up saying no. So that's why we had to escape from this. And finally, there's the more political alternative, that is to invite observers. For some of the use cases, what corporations end up doing is inviting others. Like if we are building, for instance, the corporate bonds use case in a Corda network where we are only 3 banks, you invite some telco friends, some insurance company friends, and some regulators to join the network in order to have more nodes and increase the security and the probability of collusion in the network and someone messing with the data. So this is what we were doing, and a lot of people were doing in this setup. And what we came up with was, we thought, okay, so if we want to build a federation of these corporate DLT networks, what are the layers that we would need in order to make this happen? And we came up with these different layers, where the application layer is just smart contracts deployed, or the specific use cases deployed in the different networks of the federation. We wouldn't tackle this in this moment, but we were planning to do it in order to offer interoperability. Then we defined what would be where we were going to implement our protocol stack that we called VTN, because of the virtual trust network. We wanted to give virtual trust to the networks in the federation. And here first we required a naming system, so that we aggregated every resource in the federation, and we could identify every resource in the federation, like storage, users, identities, without having to rely on the specific implementation of the underlying platform. Then we have the actual networks, so the networks that comprise the federation, what we really badly called consensus. that we also call the overlay transport, that in the end is an overlay control layer that orchestrates the communication between the different networks in the federation. And all of this overlay control has to be built over a common transport layer, because, I mean, Corda networks, Hyperledger Fabric networks, Ethereum networks, they don't use the same peer-to-peer communication. So in order to make them be able to communicate between each other in a federation, we require a common transport layer, and we will tackle also this layer. And this transport layer, what it would abstract is the actual storage that is platform dependent, because Corda doesn't have, like, it stores information in a way, Ethereum and Hyperledger Fabric did it in other ways, so we needed a way of abstracting this specific implementation so that this VTM protocol stack could be used to, I mean, to federate any kind of network. So this is just an abstraction we came up with in order to tackle this problem of federating networks, to give data integrity to the information stored in the underlying ledger blocks or whatever the platform has. So these are all layers. Actually, a fun fact: the common transport layer in the reference implementation that we had, it was a lib peer-to-peer. So we're going to see this in a moment. We launched a lib peer-to-peer node in order to have this common transport layer between all the nodes in the federation, to be able to communicate between each other when they are part of the same federation. Let's start with the naming system. Why do we implemented this ID or naming system? It was just a way of I mean, as every platform has its own implementation of blocks, of identities represented with different cryptography. Some have smart contracts, Corda has flows. So in order to have a common way of referring to all these resources in the federation and aggregating all of them, we came up with this naming system. We got inspiration from the decentralized identity standard from the DIF. It's not exactly the same, but we wanted, just in case the DIF ended up pushing the decentralized identity standard as our de facto standard, we wanted to be as close to it as possible. So in the end, to name every resource in the federation, we use the ID prefix, the ID of the federation, the network ID, so that we know what network to ping and to dial to access to that resource, the different types of resources. Initially, we only had service, that are smart contracts or flows deployed in the networks, block, that is the unit of storage in the different platforms, DLT platforms or network in the federation, and then user, that is the identities in the platform that could be identified with different types of cryptography or keys. And then we had also another resource type that we will see in a moment, that is the control block. That is this piece of information that we would use to give data integrity to networks in the federation. And according to the specific resource type that we're referring to, the ID for that resource is generated. Like, for instance, of course, for blocks, this ID is just the hash of that block, and so on. So it was a way only to uniquely identify a resource in the federation so that we could discover it and use it independently of the network where it was stored or where it lived or whatever, so that the transport protocol could discover it. We have this naming system, we have the networks now, and we have the transport layer to connect the different networks. Now we wanted to have what we again badly called the consensus, the control overlay, that is the protocol built over the lib peer-to-peer transport layer to give data integrity. What was the data integrity that we wanted to give? So imagine that we have 3 networks in the federation, network A, B, and C. A has 3 nodes, B has 5, and C has 7, whatever. So each node stores a different state, so has a different storage that it's updated event after event. If at one point there's a collusion in network A, and I'm alone in the node and everyone is colluding against me because we are only 3 nodes, I don't have, if they start messing with the history of the ledger and they change things, I don't have a way of saying, hey, the real state of the ledger is the one that I'm having and not the one that these guys are trying to push, that they're colluding against me. So what we came up with was to leverage the different networks in the federation to leave small pieces of our ledger in all of them. So we would leave small pieces of our ledger in state B, in network B, the same in network C, so that we could in the future collect them and show that our state is the actual valid one, and that there was detect that there was a collusion or some kind of attack in the data integrity of my own network. So this is the idea that we wanted to push and what we wanted to actually fix, because we saw funny things happening between companies in small networks. And how we achieved this was through the generation of control blocks. So imagine that we have our 3 networks and we set up a period of generation of control blocks of 4 in network A. So every 4 units, 4 updates over the storage, it could be transactions, it could be flow updates, it depends on the DLT implementation. Every 4 transactions, that is the period of control block generation, we would broadcast this control block to the other networks in the federation, so that we would store the information of our ledger in other networks so that we could recover it in the future in order to show that our network was attacked or not. So what we're including in this control block is a proof of history of our ledger. This is the information we included in these control blocks, where this is the unique identifier for a control block. We see that the resource type is the block C to identify it as a control block, and the identifier is the hash for the content of that control block. And these control blocks are signed from the source network. In these control blocks, we included the origin, so who was the node generating this control block from the source network, the number of blocks. In this case, if we have a static period of block generation, we would have, like if we have a period of 4, the number of blocks including protected by every control block would be 4, 8, and so on. But the reason why we included this is because in certain environments, in order to adapt to the congestion of the network and the amount of traffic being supported by the different networks in the federation, we had an adaptive scheme in order to change the period according to how congested the networks in the federation were. So that's why we included this number of blocks, so that we know the number of blocks that were protected through this control block. Then we have the number of construct blocks that is sequential in order to know the history of control blocks that have been generated in the source network. We have the ID of the previous control block so that we can discover it, and also we can check the integrity of it. And finally, we have the proof of history. As I said, the proof of history in the end is a cryptographic summary in order to validate that we are consistent with the history of our ledger. We could have come up with a lot of things for this, but we ended up going for the easiest to implement, that it was a sparse Merkle tree, in which imagine that we have a period of 7, we wouldn't include the 7 transactions in this Merkle tree with the root of the previous proof of history that we generated. So in this way, we are able to protect from these 3 transactions. We are not leaking the information of these transactions or these updates in our own network. And this is the proof of origin that we include in the control blocks and broadcast to the rest of the network, so that we leave this piece of our ledger in other networks in the federation in order for us to validate if someone has touched maliciously our data. Again, we could have come up with more, probably with more advanced methods, but this was part-time research, and we ended up going for the easiest to implement. Another requirement that we had is that we didn't want to fork the base code of the different platforms in order to embed this control overlay and this protocol. So that is why we came up with the concept of a daemon, so that not everyone had to run this protocol if they didn't want to. and so that we didn't have to, we just had to implement a driver between the DLT platform that we wanted to support, and so the abstraction driver between the daemon and the actual DLT platform, and we didn't have to touch in any way the base code of the different platforms. So the daemon in the end is just a peer to peer node that runs this protocol that I'm describing, and it's not mandatory. So if for instance, we have 3 banks in this network A, maybe only one of the banks would run the daemon because he's the one that wants to give additional security to data integrity because he doesn't trust the other ones, and he would become part of the federation with all the other nodes in other networks that are running this daemon in their own network, C, D, and so, as I said, we generate control blocks that we broadcast into all of the networks in order to leave pieces of our ledger. And how is this done? So every control period, we just broadcast the control block to all the networks in the federation through the daemon. And when one of these daemons decides to accept the control block and store it in the ledger, it would send a signed acknowledgement to the one that sent the control block saying this, it's like a receipt. This control block was stored at this timestamp in this network, and this is the acknowledgement, the signed acknowledgement that actually you can check that your piece of the ledger is stored in my network, and you will be able to access it in the future. In order to track all the control blocks generated and all the acknowledgement received from other networks so that we can validate our ledger in any moment and like check that the control blocks are still alive in other networks, the daemon also had this registry in which it stored the identifier for the control block, the content included in the control block, and the different receipts, acknowledgements received from the networks of the federation that decided to accept the control block and store part of someone else's ledger in his own storage. Apart from this block generation process, the daemon also includes this is more an implementation detail. It also includes what we call liveliness process, in which it periodically checks if if it still can dial other networks in the federation or the ones that are storing part of our ledger, because we're talking about corporate environments with a lot of firewalls, a lot of configurations and security measures. So we experienced that in many cases, some networks we could call in the past weren't dialable in the present. So that is why we added this liveliness period, in order to check if the networks were alive, and in case a network wasn't alive or our control block wasn't available anymore in the ledger, we could broadcast again the same control block in order to update the receipts and the number of control blocks stored in other networks of the federation. And this protocol could be configured considering 4 parameters. First, the number of independent networks that we require to store control blocks, that this was the KC. Then the period in which we would generate these pulses of control blocks, the number of liveliness blocks that we would check. So in this registry, we would sequentially check every liveliness period. We would check a number KL of acknowledgements to check that we can still dial the network and we still can access that resource in the federation. And as we didn't know which were the best parameters to choose for the protocol in order to have enough protection to our data integrity according to different scenarios in the federation, number of nodes in the network, we came up with what we called detection trust index, that in the end is just the probability of abusing this protocol, and the probability of attackers to attack this protocol and mess with our way of validating data integrity. We got inspiration for this profiling of and these statistics for the detection trust index from some papers that profiled the the probability of attack over Bitcoin, over the Bitcoin ledger. And in the end, what we said is that this detection trust index would be 1 minus the probability of collusion in the block generation process and the probability of collusion in the liveness process, because those are the two windows in which someone can forge receipts into us and make us think that we have our data protected in other networks in the federation, and it may not be the case. So we ran some simulations considering this detection trust index for different values of KC according to the number of malicious nodes in the federation. We checked how this alpha collision, this probability of collusion, was affected by the rate of malicious nodes against total nodes in different federation topologies. We checked how the detection trust index behaved for different numbers of KL and KC, TL and TC to see what was the best number. And in the end, what we came up with is that with a KC of 2 to 5, we protected with 99% the integrity of our data, that the TC should be between 30 seconds and 5 minutes, but this was really use case dependent. I mean, these simulations were really limited and only focused on the protocol, so we didn't bear in mind all the potential attacks and the dynamics of the networks in the federation. So it was really limited. So we wouldn't bet on this for sure in an open environment, but we have to bear in mind that we are in a really relaxed environment, that is the corporate environment where attacks are rare. I mean, are rare, but when you have attacks, they are more social attacks than actual technical attacks. And this is all that I wanted to share today. I mean, I had a lot of potential future work for this, because in the end, it was a 6-month research, part-time research. So it was in a really early stage, but at least we managed to have a reference implementation, as I've said, having the transport protocol over lead peer-to-peer and with the overlay control working with 3 networks in Hyperledger Fabric. I would have loved to try having different type of DLT platforms, so not just Hyperledger Fabric, but also Corda and other DLT platforms and implementation to see how it behaved, the protocol with different platforms. But in the end, my assumption is that it would only affect, so once you abstracted the storage from the specific implementation of the storage from the transport layer of in the daemon, it would behave in the same way, either if you have Corda or you have Hyperledger Fabric or you have a Hyperledger version. Another thing that it would be great to check is the benefits of, as I advanced, the benefits of the naming system in order to have interoperability between the different corporate networks, because right now what we're having is a common transport layer in which we can flow messages from network to network signed with the same standard protocols, so that we could access resources from other networks instead of going like the snapshot that some are doing with public networks outside. Once you have the same transport layer, you could send actual, not on-chain, but at least protected and signed messages through the common transport layer. And also, I would have loved to explore attack vectors to evaluate the hardness of the protocol, and not just this limited theoretical analysis and simulation that we did. Because actually, quoting David, that he says that decentralized networks are also social networks, I completely agree with him. And I would add that once you start playing with decentralized networks and DLT networks in corporate environments, you would realize that in corporate environments is even more a social network, because you will end up having a bank that participates in several networks from several use cases, and that is friends from other entities that also participate in several of these networks, so that it's really easy to, I'm not saying that they will do it, of course, but it's really easy to try and collude between different socially connected parties in different of these limited number of nodes, networks for specific use cases. So that's why we embarked on this specific research. And finally, the line that I was launching before leaving Telefonica was because, as you've seen up till here, what we're doing is just detecting if there was an attack or there was some kind of malicious or unintentional change between several parties in the data integrity stored in our network. But one of the things that I was also exploring is to build these proof of histories so that not only you're able to, by collecting this proof of history, to check that no one has touched your data, but also you're able to reconstruct your ledger so that you could restart the network in an environment in which it has been completely attacked or completely made useless. And this is it. Thank you very much for listening. And if you have questions, you've been pretty quiet.
A really quick question, not on the technical side that much, but what was the kind of killer use case for DLT as seen by kind of the corporate world and Telefonica in particular? Was there like interest to, you know, like only for financial activities, or put them like deeper into like technical works like the telecoms and, you know, content delivery networks and things like that?
So, I mean, that's a great question. The success cases were in finance, in supply chain, and also internally between telco companies to agree on things that usually they don't agree, and they end up spending a lot of money on like conflict resolution. So an example is the supply chain from Telefonica. It uses blockchain because they ended up not being able to track where devices lost in all of their supply chain. So when they send you the router home, they didn't know where were lost some of the devices that were lost. So they started tracking all the supply chain in blockchain so that the different entities involved in the supply chain had to update a common database. So in the end, all the success cases have been companies that don't trust that much, at least between each other, or they don't know what is happening and they want to update a common state.
Mm-hmm.
So it's more, that's why we were that focused on data integrity, because they use it as a common database between different entities.
And the stack that you proposed, like, did you find any difficulty in like getting all the partners in, you know, in some group to adopt it, or did you have to go through some standardization process?
Not a standardization, but like that is why we made it. So our role here was as an infrastructure provider. So we were giving like the nodes and the infrastructure for the different use cases. We were building the networks, and what it happened is that they wanted so they were in a way of checking that no one had touched the history in the network. So we were the ones suggesting certain partners that were deploying several networks with us to have this daemon and build this federation between them, because so imagine that we have a bank as a client, that we build a network for them for several use cases, but these use cases end up having just 3 nodes.
Yeah.
We suggest them to launch this daemon in their different networks they have and they're participating in that just have 3 nodes, so that they can leverage the number of nodes of other networks to protect the data integrity of their sub-networks, so that even if in one of the networks they are participating, there's a pollution and there's someone that is trying to mess with the data stored there, he can check if there was some kind of pollution and he can detect where that modification came from.
Yeah.
I don't know if that answers your question.
Yeah, it does. Yeah. Okay, very interesting.
Anyone else?
I have another one. So in the decentralized identity part, given that it's a kind of corporate world where, you know, identity, like, as you said, the supply chain, you want things to be directly identifiable. So how and where was it used? Like who had an idea, like, you know, what actors in the system had a kind of decentralized identity?
That's a great question. So it depends on the specific use case. For some of them, there was a fine-grained identity where every user has their own identity, but in others, they just have a common app that they just use one identity. The reason for this standard way of treating identities is that, again, you have a single entity that participates in different networks, and these networks implement different DLT platforms. So they ended up having to have a wallet for each of the platforms. By standardizing the ID, you have just one identity to manage all of your identities in this federation. So that's why we talked about interoperability. Actually, we launched in Hyperledger this approach, like we this same DID approach for several network. We open sourced the project, and it's in the it's a Hyperledger Lab project right now, to have just one wallet for one corporate wallet for several DLT networks with different identities.
Interesting. Okay, got it.
Anything else? Anyone else? All right, Alfonso, thank you so much. Really appreciated you giving this talk to us. If you're watching on YouTube, please remember to like and hit the subscribe button. If you want to suggest a topic or a speaker, there are instructions on how to do that in the description. We'd also love to have you join our mailing list, where you can receive quarterly newsletters, future talk announcements, and information on research funding opportunities from Protocol Labs. You can do this in the footer at research.protocol.ai. Our next talk is Monday, September 28th. That's this coming Monday at 17:30 UTC, 5:30 p.m. Universal Coordinated Time, from Alberto Sanino, who is a research scientist at Facebook Calibra. His talk will be about FastPay, high performance Byzantine fault tolerant settlement. Thanks for joining, everyone. We will see you next time.